It's a very long This is so messed up. It was like, wow.
Okay, we're live. It's working. How's everyone doing? Okay? Huh?
My computer's blue screen twice trying to get converted simulations.
Oh, sorry. I'm sorry. If you think you're the only people that are experiencing difficulties with Ansys,
I know we're not.
we're not. We think we're the only ones. I think it's a little bit of a universal thing. But I do feel your pain. And I have felt your pain as I've also worked with Ansys. So this is tough.
The third time I'm remaking the entire simulation because I think it's corrupt again. I promised to advertise for it. Everybody.
We're recording this. We will not say ill of our friends. Okay, so let's go ahead and discuss what we're going to discuss and then discuss it. And what are we discussing? Well, we're going to be talking about fluid structure interactions today. And so, Spencer, I may feel the pain you're experiencing in a few minutes, okay? Because I am going to attempt to do a live Ansys demo. And if I fail, please have mercy on me, okay? Okay. And you're probably like, well, please have mercy on us too, right? Because we grade the stuff that you submit. So we can all try. We're gonna do a one-way fluid structure interaction example. We're gonna attempt to do it, and then I'll talk to you a little bit about what we do in our lab. In terms of what's happening for the rest of the course, though, it's exciting because I don't know. Actually, is it exciting? I hope. Not exciting. Okay. Well, you all are Group A, right? So originally you had a day off near the end of the semester because you were one whatever you call it, class ahead of the other, which would be Group B. Nonetheless, we are going to have a special guest alumnus come in on the 29th. Okay, so that was going to be, I think, your day off. Okay, but instead you're going to have no class on the 24th. Okay, does that make any sense at all? So the syllabus says that you have no class on the 29th, but no, or actually I don't know what day it is, to be honest, now that I think about it. But there's going to be no class on the 24th, and then there will be class on the 29th, and so you have a guest speaker. They're going to come in and talk to us a little bit about Ansys in the workplace. They're at Pratt & Whitney, and they're going to also work out a small demo, and we'll have a little bit of an assignment. May 5th, El Cinco de Mayo. All right, it's a big one for us. That's the last day of classes. Try to get ahead of it. Why is it a big day? Well, some of you may know already you're supposed to watch 4 of the virtual guest lectures. Okay, that's been up for a while. Well, the semester ends on May 5th, so make sure you do that and comment before that day. The final project is due that day. Okay, the final video is due that day. So that's quite a bit of effort there. The good news is that we have what I think should not be intense assignments in the lab now. So we'll have a lab a week from, or on Tuesday, right? Which will be based on what we covered today. That assignment should be due about 4 p.m. I'll release it. I think it's doable. We'll see. based on what happens today, maybe in part. And then there'll be one small lab based on the guest lectures. Okay. So no more like big post lab, no more like trying to get your airflow to work. Okay. No more heat transfer off a wire. Okay. Those types of things. I think the lab simulation should be pretty calm going on. Okay. Any questions about what's coming up? It's a lot. It's a lot. Plus side, no final. Right? That's a plus. Okay. So if there are any questions about it, just let me know. So for the demo, okay, this one comes from Rahman and Pejman, prior TA, Ansys extraordinaire, and Professor Singer. Now, the video, they have an unlisted video that you'll be able to get access to, and they did it in 2022. When I've done it in 2024, I have found that there are some little like buggy things that happen. I think they're like different. Anyway, so hopefully, all right, I'll be able to kind of just flag what some of the weird things are, what you can ignore, and we'll see if it works. All right. So the idea here is that there is a beam or a wall, okay, that's being hit by fluid flow, okay, and well, if it's like, I guess if it's this way, like this, right? What do you think is going to happen to the beam? If the flow is this way, what should happen to the beam? Well, maybe what should happen to the fluid flow? There's a beam here, right? You see the beam, 50 millimeters tall. This is from their thing. What should happen in the simulation?
So the flow should increase because it's going to run through a smaller area.
Yeah, okay, so just to constrict a little bit.
Pressure should decrease, and there's just going to be area near the bottom with no flow. It's going to like gradually decrease.
Okay, good. Yeah, okay, and then what should happen to the beam?
It should deflect to the right there.
Yeah, okay. So if we do this right, okay, like Matt has suggested, right? This is what you should get for a 2D perspective. Then we put it in a slightly 3D perspective, so there's actually a little bit of thickness here. Same deal, okay? Looks very similar. And then we should see the beam, that's that middle piece that's been missing, deflect. Okay? Now, what's aphysical about this problem? In other words, what does not make sense about what I just showed you? That's the fluid flow. That's the deflection. That's the fluid flow. That's the deflection. Yes, okay, what's up? Spencer.
The beam doesn't deflect with the fluid flow, so like in the fluid flow simulation, so it won't really reach a steady state. It'll kind of just reach a state based on that maximum force.
Okay, whoa, so wait, the first thing you said, I'm still stuck on the first thing you said, the beam won't really deflect. What do you mean by that?
Like, what I mean is in the fluid simulation itself, I don't think the beam actually deflects in that part of the simulation.
Oh, yeah, right. Got it, yes. So what you're saying is here, it's still 100% not deflected.
Yeah.
Okay? But here, it's deflected. Okay? So, what you're saying, right, is that deflection should affect the flow, which then affects the pressures that are being exerted on the beam, right? That would be what we call two-way coupling. Yes, Bobby. So we're at 1,000, Reynolds number 1,000. Okay, so we will run turbulence. Okay, but it's not. Yeah, we don't have as much with the vortices and stuff. And this is steady state simulation. Okay, so even then it can be difficult to see vortices when you're running steady state. Because it's an average, it's the Reynolds average, Navier-Stokes average. Reynolds average Navier-Stokes. Okay. Good point. All right, so this if it came back, right, and we said, okay, now you gotta redo the fluid simulation with this new deformation, and you went back and forth, that would be two-way coupling. would one-way coupling, so we're doing one-way coupling. We're saying this is the state of the fluid, this is what the fluid is going to be doing given this geometry, and this is the deflection. When would one-way coupling be a very reasonable thing to do here? I agree. This looks a little extreme, right? Like if they have that much, I'd say you got to go back and do some more work, right? When would this approach? So this is called one-way, right? We're talking about one-way FSI, one-way fluid structure interactions. When would this approach be okay? Yes.
If there's not that much deflection.
Exactly, right? So you see here, two options for the material, steel and silicone. All right? I showed you an option when we're using the silicone. But if you use the steel, you can calculate the stresses in it. It's not going to deflect that much. And we'll show you that if the demo works. All right? We'll show you that today. Okay? And that would be a pretty good assumption. All right? So let's get to it. Let's see if I can make this work. So we're going to open up Workbench, and what we're going to do is first run a 2D simulation, okay? And then actually we'll show you, Rahman does a nice job of taking that 2D and showing you how you can create a 3D, right? Essentially, pool it, copy and pool essentially the thing to have some thickness, and then run the simulations again, right? So we're going to be first working with Fluent, and then later, if we get it to work, we'll get Fluent to talk to static structural, and that will be the one-way coupling. Okay. So here we go. We're going to do geometry 2D, and we're going to open up SpaceClaim. And while SpaceClaim is doing its thing, let's analyze the geometry a little bit here. We're going to be 200 millimeters wide, 100 millimeters tall. Okay. We've got 1 centimeter per second for the flow on the inlet, and the Reynolds number is going to be about 1,000. So how is that calculated? Well, that was calculated by, let me see if I've got it. Oh, pen. So the Reynolds number here, if my pen will work. Oops. No. Okay, let's see what happened. Whoa. Okay, so the Reynolds number is going to be rho times velocity times some distance, okay, or some length. You gotta be kidding me. This has happened before, when everything, oh no, oh no, oh no. It was bugging out a little bit before. Let me try this other cable.
See, that makes sense. No, it works. It takes so long.
What's up? All right. Sorry, it works. All right. So so we get rho VD over mu for the Reynolds number. Density of water, anyone? 1,000, right? Kilograms per meter cubed. This is going to be 0.01 meters per second. And the distance we're going to use is going to be this 100 millimeters, that height. So this is going to be the 0.1 meters. The viscosity of water. Anyone? Fluent database, click, water, liquid, copy, close, forget about it. All right, that's what we normally do. Okay, so the viscosity of water is 1 millipascal second. Okay, so 0.001 Pascal seconds. All right. So all right. So now let's get to the geometry. In space claim, we go ahead and we click on the Z. We click on the sketch plane. We can click on that again, I guess. We click on the rectangle. We're going to do the 200 millimeters wide, 100 millimeters tall. That was just a tab. And then enter. And then we'll put in that center pillar. So you can come over here and it says a center line. All right. And we'll click on that. And then we're going to do 5, hands off mouse, tab, and then we're going to do 50, enter. Okay. Then we come over here and we hit the select button and we drag it over the geometry. Okay, and we can click fill. All right, and it does this. Then we come over here to the surface and we're going to detach them, detach all. Okay, because we want to. We want to be able to separate the fluid portion from the solid portion. So we hit detach all. And now we see we have 2 surfaces. This one is we're going to rename it fluid portion. And this one right here is the solid portion. Okay, and Rahman says we click that box to get rid of that so we don't have that activated. And we should be able to go. So we just do close on that. And that should bring us back into Workbench. Okay. For the mesh, when I've double clicked on this and started doing the meshing, I get an error. Okay, maybe it will come up, maybe it won't this time. That was something that was kind of unique compared to, I guess, what happened in the 2022 version. So what I do is I just close it and I try again, and that seems to have taken care of the error that came up. With this part of the problem, we're only going to be looking at what's going on with the fluid, right? Because we're doing the one-way coupling, okay? And so first we're solving the fluid problem. So this is kind of like a problem where you have fluid over, an internal body. And we're not going to do the deep convergence, right? You like, oh, what's the height? What's what? Okay. So let's see. It's still thinking. And when we go back, let's just go back here for a minute while it's thinking. The fluid flow rate, the inlet. Well, we're going to end up specifying inlets. We're going to end up specifying a fluid structure interaction boundary around here. This is going to be the outlet. And then we're going to have symmetry, okay? So that would be like a no shear condition at the top. There's going to be no slip, which is essentially a default for Fluent, on the bottom. Okay, let's see how this is going. All right, so this is the error that it threw at me before, okay? And it didn't really, maybe it'll work. Let's see. Let's see, I don't see anything. Nope, it wasn't. So what I did is I just closed this and did the process again. Okay? So what your lab is going to be this, essentially, by the way. So that was the other reason I wanted to do a demo. And I was like, well, I could record it, or we could just do it here. And given how things were going, I decided that we'll try to do it here. So that should be closing, and then now we'll just double click, or I right click or edit, and we open it up. And it should work. Okay, and so now it comes in. I don't know why that happened, but this is good. All right. So we want the fluid, but we don't want the solid. So we're going to go ahead and we're going to suppress this body. Okay, and then we can go ahead and we can name our inlet and our outlet and our various boundaries of importance. So if I left click on that after I've got edge select and then hit N, and we'll call this inlet. This is a reserved name. This top one, N, we can call it symmetry. That also is a reserved name by Fluent. Click on this one, hit N, type in outlet, also a reserved name. And then we need to select, so we did this one, and then control. Okay, I guess I didn't. I thought I got the middle. I guess I better zoom in. Right, like that. Okay, so those three, and I hit N, and I got, we'll call this FSI. So that's going to be where the fluid structure interaction occurs. We hit OK. Then down here, okay, so we should see those are where we want them to be. We go to mesh, and in this case, we're going to use an element size of 1 millimeter. So your settings might be a little bit different. I'm in metric millimeter, right? So if your settings are different, then just make sure you get the right units there. We're going to actually add an inflation, okay, where the no slip boundary conditions exist. Okay, so first we select that whole thing, then we select, oh, but I have to hit apply. Oh, no, well, first I have to do that, then I have to hit apply. Then we're going to select here, well, this one, control, this one, control, that one, and that one. Okay, and we hit apply. We should have 5 edges selected, and we'll go up to 5. Okay, now we can generate the mesh and take a look. While this is happening, you might recall that you can have you can use a y plus calculator when we looked at this okay, or y plus distance estimator, all right, and we're gonna use it for the 2D, but we're gonna ignore it for the 3D actually. So you can type in the free stream velocity, which is be 1 centimeter per second. The density is 1,000. This is air though, right? We said that we had 1 e to the minus 3 for our viscosity. The boundary layer length, this is, we can say, well, you got like, is it 0.1 meter or 0.2 meter? We'll just put in 0.1 meter, okay? We keep the desired y plus value at 1, and we estimate the wall distance. Okay, so this is saying that we have a Reynolds number of about 1,000, which we do, and for that, you want your estimated wall distance. So this, you want to make sure that your your layer right next to the wall is less than this number. So this is 0.97 millimeters. All right, so it's got about 1 millimeter. So once this thing has been meshed, okay, you can see that it's refined along these no slip boundaries, and you can go in here, and this is not super precise, but you can click on the node, and we can click on, say, that one and say that one. Whoops, I said I had to hit control. Now I got neither. Okay, and you see down here, it says it's 0.18 millimeters, okay? 0.19 millimeters, and what did we say? We said it had to be like 0.9 millimeters was what we were aiming for. So the thickness of our elements right next to the walls is less than what you want for your y plus. We'll ignore this in a little bit, okay? But it's just good to have a reminder about this this behavior. Okay, so we're good here, and we'll go ahead and we'll hit update. And this has been transitioned or translated to Fluent appropriately, okay? And or it's ready for Fluent, I guess you could say. It's going to Workbench, and in Fluent, we're going to use the K epsilon turbulent model. Now, if you like, you can look like K epsilon, K omega, and again, we're doing kind of an impressionist perspective, okay, on a lot of these things at this point. But if you look at, okay, which should I use, K epsilon or should I use K omega? And if you read this, right, what it tells us is that, okay, it's solving for turbulent kinetic energy and epsilon, or the rate of dissipation of turbulence kinetic energy. And the nice thing for us, all right, is that, see this word, we like that, or that phrase, good convergence, all right? So it may not be super accurate, and we're not necessarily going for accuracy in this demo, but it has a good convergence rate. So this is maybe one that we might want to attempt first. K omega, right, it says more difficult to converge than K epsilon. Okay, so that gives you kind of a hint. Maybe I should try K epsilon first. Okay. Okay, so now we go into. Did I not? Oh, I should have clicked on Fluent earlier. To Fluent. And we'll go ahead and we'll do double precision, and we can up it to 4 cores or processors like that, and we hit start. And this is just a 2D simulation, yeah, but what we're going to do here is we're going to get a perspective on what's happening with the 2D flow, and then we're essentially going to make a 3D slab, okay, of it's going to look like a plane strain problem essentially, okay, and that plane strain problem actually is going to involve a 3D solid model. Okay, so we're doing the 2D problem to kind of get an idea of what things should look like, kind of in a thick 2D slab, okay, and then we're going to extend it into 3D. So that we can solve the solid mechanics problem in 3D. if that makes any sense. Okay, so here, what we're going to say first is our model, right? So it's got SST, K omega. We're going to go ahead and use K epsilon. That's what Rahman did. Okay, and for the materials, we can look at our fluid material, which is only air. So we'll go ahead and we'll put a new one in. And we'll go into the Fluent database. And we'll go down to water liquid. And we'll hit copy. And just to see right, the viscosity is 1 millipascal second, right? Or it's 0.001003. All right. So we close this, and we can close this, and we see now that we have water liquid. We come over here to the fluid zone, and we can double click on it if we want, or we can right click on it and hit edit. So we're going to change to water liquid, apply, close. For the boundary conditions on the inlet, okay, we're going to have a velocity of 1 centimeter per second coming in on this side. And so we'll come over here and we'll change that to 0.01 meters per second, apply and close. Okay. This is set, the outlet is set, symmetry, okay, should be set, and the walls are all, we can double click on them, but the walls should all be no slip condition. And we shouldn't have to change them. Stationary wall and no slip. Okay. So we come down a little bit further, and we're going to go to the run calculation. So we double click here, and we can go ahead and up our number of iterations. We're not going to use all of them, okay, but go ahead and put in a number there. Greater than, I think, 50 or so, and we right click, and then we can hit initialize and calculate. It's going to use the default in this case, which is a hybrid initialization, and it should solve pretty quickly. Okay, so 50, less than 60 iterations it took. Okay, and if we come down here to the graphics, we can click on contours, right click, new, and we'll look at the velocity, and we'll save display and close, and that looks pretty good because we've run it before. So this is, you probably can't see it. I'll go ahead and copy and paste it. Try to, okay. But this is, well, actually I know what it is because I've done it already. Okay, it's about 2.7 times 10 to the minus 2, so 0.027 meters per second as the maximum. And that lines up with what Matt said at the beginning of class, right? You were saying, hey, it constricts the flow, okay? And so we expect it to speed up. So it goes from an inlet flow of around 1 centimeter a second to now over 2 centimeters per second in this region. And it's slower, okay, pretty stagnant down here behind. Now, no, don't do that. Please, okay. Last time that crashed everything. So let's go back here and we'll just work here and see if we can get through things. Okay, so this is pretty good. We'll go ahead and close this. And we can hit OK here. Often I say use it, keep it for future, but in this case we can just, the top option is fine. So now we go to Fluent, or this analysis, and we're going to right click here and we're going to duplicate. Okay. So duplicate, and this is going to lead us to transition to 3D. Okay. And again, the reason we're making the fluid flow 3D is just so that we can use 3D structural analysis, or static structural, down here in a minute. So it's thinking about it, deciding whether or not it really wants to do this, and then we click here, and it's 2D geometry, but we're going to change that to 3D. Okay? and then we're going to open up the geometry in space-clay. So we're going to specify a thickness or a width if you want. So we got this 2D flow, and we're going to kind of pull it out and make it 1 millimeter thick. And we're thinking. All right. So good. It looks like okay. It looks like it's come in. That's pretty good. All right. So we can kind of rotate it up. We can zoom in a little bit. All right. And we can move things over, and we can kind of select everything, and we can do a pull like this. Okay. And we click there, and you remember if you hold it up. My left finger is on the mouse still. I hit 1, okay, and then I hit enter, okay, and it's almost still 2D, all right, but it is in fact 3D now. You can see there's some thickness there, okay. In this case, all right, I needed to do pull no merge. All right, so we saw that. All right, so let's go ahead, undo what we just did, come back here, and we do no merge. Okay, and then we do a pull. Now do 1. Okay, now there are 2 solids. All right. Once again, we don't want both solids. I mean, we don't. How do you say it? They're not both solids. One's fluid and one is not fluid. So this one is going to be renamed to be fluid, and this one is going to be renamed to be. Or it's not, it doesn't need to be renamed, it's solid. Okay, that's the middle section. Okay, I'm not quite sure if this is superstition or what, but if you click on this, I think you're supposed to click on that. Okay, well maybe not. Okay. There, it's activated. So it's supposed to be, you're supposed to click on that, and then we hit close. Okay, then we go ahead and we're going to work on the mesh. Now, in the mesh, there are going to be a couple things that we have to do. We're still looking only at the fluid portion of the problem. Okay, yes. Would you like to? Yes. Okay, so we're going to take the updates. But you remember those name selections that we had for inlet, outlet, symmetry, all those, they were before applied to edges on the 2D problem, but now we're going to apply them to the faces, okay? And so we'll come up here to the geometry. Okay, we're still waiting, I guess. Still waiting. While we're waiting, I don't know if I want to do this, if it's going to require. Okay, great. It stayed. It did not disconnect. That's good. I was worried it was going to disconnect from the screen. Okay, so here we are. All right, it's giving us some kind of like, whoops. It's giving us some kind of like mismatched scope business. This is a newer thing. I don't really look at this that much, but it highlights. It's newer than 2022 at least. And so when you come into here, you'll see like it's saying, hey, there's an issue there. Okay, but let's first go ahead and we're going to suppress the solid again. Okay, so we're going to suppress that body because we're only interested in the fluid portion. And we're going to come over here to our name selections on the plus. And the inlet, it's like, hey, there's a problem. So now we're going to use our surface or face selector. And we're going to, oh no, okay, attempt, there we go, to select that face. And then we hit apply. And then, so now our inlet is that. Okay, and then over here, It's hard to see again, all right, but we're going to click on that face. We're going to hit apply. Okay. And over here on the back side, we can go ahead and we can select this face for the outlet and apply. And then down over here, we're going to make these FSIs new. Okay, I didn't even remember it had a couple. Okay, but we're going to select this one, hit Control, and then hit, whoops, not that. Hit Control. Okay, so we should have those 3 faces selected. Apply, 3 faces. We're good. Okay, it remembers that we wanted 1 millimeter mesh. Okay, and so that's fine. Now though we're going to take the opportunity to essentially tell it that we want it to have a mesh that sweeps through the thickness of the part. Okay, so we're going to, first we're going to ignore the inflation. All right, so this is where we did all that nice y plus calculation work, but we're just going to ignore it for now. So we're going to suppress it, and then we're going to insert a method that is going to apply to this entire geometry, and we're going to use a sweep. Okay, and what it's going to do is it's going to sweep through this with a quad. We're going to say all quad, so it's going to look like, you know, it's going to have square elements on here, and we're going to do this not automatically, but we're going to use a manual source, which is going to be this face, like that. Okay, and then we hit generate. It's not associated with any geometry. What? And this may be, this is a new one, I'm not sure. So this is suppressed. Use geometry. This may be where we end for now. Yeah, we're using geometry settings, sweep method. What is it lacking? I don't know why it would, I don't think it needs sizing there. Okay, so that's, no, I want it on the whole body. Okay, so that's body sizing. That's 1 millimeter, that's fine. 1 body. Oh, it's because, blast. Okay, because I hadn't hit apply. Feel free to yell at me when that happens. Sweep method. Click on this face, hit apply. Now we've got a face. Now it should be able to generate. Thanks for bearing with it. Okay, so now the mesh, yep, it looks pretty good. Okay, it doesn't have the inflation, all right, that we had on the other one. We're kind of ignoring that issue, right? But you can see it does go through the thickness, and it's just one, essentially one element thick. Now, for the, actually, I should have remembered this. For the, earlier, but for the symmetry, okay, you recall that we were looking at a 2D simulation, which is essentially a thickness, like really thick slab, now, since we've added a thickness to this simulation, what we actually need to do is we need to extend and say, oh, we don't actually want no slip. Like, we're not trying to get the water to squeeze right through this 1 millimeter thickening. We want it to essentially be a 1 millimeter thick representation of a very wide tank. Okay? And so to do that, what we say is we do symmetry, just like we had no shear, okay, on this top surface. We want to add that to these other surfaces as well. Okay, so there we go. Okay, so we've selected them, and now, actually, I think I probably need to select the top one as well, just to add to the fun. And here, instead of it being 1, now it's going to be 3 faces. Okay, so I forgot to do that earlier. I'm glad I caught that. All right, so this should be good. Let's go ahead, I guess, mesh. I don't think it's going to change anything there. Let's go ahead and update the workbench. And the mesh has been translated. Excellent. So now we close. Let's go ahead and get into Fluent by clicking on the setup. Yes, we want to load the new mesh. Okay. And Fluent is going to say a couple things to us. It's going to say, your zones have changed. You were doing a 2D problem before. Now you've made it a 3D problem. So how should we handle this? Okay? At least this is, and it was a little bit different error than I saw when Rahman used 2022. So let's see. It's thinking. Okay, so it says note, 2D, okay, there were a couple things here, okay? There were a couple errors, but one is a note, 2D double precision pressure-based standard K epsilon case read into 3D double precision pressure-based standard K epsilon solver. Great. But the model information is incompatible with the incoming mesh. It says it's found some missing and new zones in the mesh. To make mesh compatible with settings, please visit this match zone names panel, file, recorded mesh operations, edit incoming zones, match zone names. All right. So what you do is maybe you copy that in case you forget what it said. Okay. But I got a note here, so I go to File. Okay. I go to Recorded Mesh Operations. I go to Match Zone Names, and then here it says discard unmatched missing zones and accept new zones. Go ahead and hit Apply. Okay, do you want to reload setup? Yes. Okay, so then what you see there is it renamed these zones. There were missing zones that they had, and then it added like a 1 there. So now these new zones should be all that we need. Okay, and yeah, we did it. It's working. It's working. Okay, so this note 2D double precision pressure-based standard K epsilon case read into 3D, so it's fine. Okay, we hit close, we hit OK. All right, and what's nice is, so it says it's out of date. Okay, that's not nice, but it's actually things are going to be just fine. And what's nice about when you do it this way is it actually remembers that you're doing K epsilon instead of K omega. It remembers the fluid, okay, that we're using. The fluid is water. If you come in, all right, so it's water liquid instead of air, okay, and it's kept everything intact. So the only thing that we should really have to do is come down here and initialize and okay, yeah, because see the other thing it did, right? So if you look at the boundary conditions, just a note. Okay. It also brought in symmetry, so it brought in those 3 surfaces instead of just the top surface. Okay, and it has the walls. Okay, fluid structure interaction walls, and it has the bottom. So we should be good to go. Okay, we can go ahead and go to initialize and calculate. And it might take a little bit longer, okay, to run. It might not. We'll see. Okay, so yeah, remember before it was done before 60 iterations. Now it's taking over 100 iterations to run. Okay, it still is disconcerting, and I mean it has scaled residuals, but there's nothing here in the visual, okay, which is a little disconcerting. But if you come over here and you go to graphic, contours, and you right click, new, and you click on, let's say, the velocity, you hit the save display, voila, okay, there it is, and it's in 3D, okay, and you know, you can kind of tilt it, you can see, yes, it's in fact 3D, okay, and if you're like annoyed that you can't quite get it back to how it was, then you can join the club, but you can click over here, and you can then click, this little thing comes up, and you should be able to click on the Z, and so now you're looking at that perspective. The other thing that's good, all right, you may not remember, but this says 2.7 e to the minus 2 meters per second, and that is reflective, okay? Remember, it was 2.7 before, about 2.74, and now, all right, in 3D, it's on the same, it's the same ballpark. This is what I copied and pasted previously. So this is good. I'm excited that we've gotten this far without a catastrophe at this point. Right now, what we'll do is we'll just go ahead and close this, and we'll say, sure, we're done. And we will go back into the workbench. And we're going to start looking at how we can couple the structure to the pressures that have been induced by the fluid flow. So for that, we bring in static structural over to the solution. And here, it now gives us an opportunity to think about what materials we're going to be using. So in the engineering data, we have structural steel, and we'll use the structural steel, okay, as our first case. And we said, remember, in one-way coupling, structural steel is probably fine because it doesn't have much deflection. But we'll go ahead and we'll create a new material called silicone. Okay? And for silicone, we'll give it some density. And we'll come over here and we'll give it some elasticity. Okay? So the density of silicone, any ideas what the density of silicone is? Close to water. Let's use it. 1,000 kilograms per meter, 1,000 kilograms per meter cubed. Now the Young's modulus, silicones can vary quite a bit in terms of how soft or hard they are. And yes, hardness and softness are not elasticity, not Young's modulus, but they're very much correlated. So we'll say that we're going to start here with 1,000 pascals. That's really, really low. Okay? And Poisson ratio, these are rubbers, and so they're incompressible. They conserve their volume, but you can't put in 0.5 for the Poisson ratio because things will explode, so we put in 0.49. Okay? Oh, except I put it in on top. Okay, so 1,000 here, okay, and then over here we put in 0.49. Okay, and then we close this. Now, for the next part, we are going to leave the geometry as it is and just go into the model. Okay? And we're going to ignore the fluid portion, and we're going to emphasize or highlight the solid portion. And we also are going to have to add some boundary conditions. So you think, oh, well, that beam was, of course, it was just fixed in that geometry? Well, yeah, well, we need to actually tell it. Okay, this is where you're going to be fixed. This is where you're going to feel the pressure from the fluid. Okay, and the walls are going to be frictionless. Okay, so we didn't talk about this too much. Okay? But imagine, see, we've got this 2D or 3D slab, but it's simulated kind of almost like a 2D system. And these walls, are they connected to more material? Well, yes, the way we're solving this problem, they are. Okay? So we're going to say that on this wall, it's like a frictionless support that it has other material going along. Okay. Yes, this error has come up for me before, and you get scared. At least I got scared, but I ignored it. Okay? So you just ignore it, and everything seems to be okay. Now, for the geometry, we're going to suppress the fluid this time, and we're going to look at the solid. Okay? And all it is this little beam. All right? And we'll go ahead and add some. Well, okay, we can mesh, and then do you want to do boundary conditions first or mesh? We'll go ahead and do mesh, I guess. So the mesh is going to be a little bit different. We're going to say here, we're going to insert a sizing on, and this is, there's no one way to mesh, but here Rahman decided to do it this way. We're selecting that top surface, and we're going to use, again, 1 millimeter. Okay, so it's going to essentially create like a little grid there. And then we're going to sweep it to the bottom. Okay, so in this case, we're going to add a method where we have the geometry, the entire thing selected. I hit apply, that's good. The method is going to be a sweep. Okay, so we come over here. And we're not going to change it to all quad this time. I guess we could, but we're just going to leave it there. And this top surface is the target one. All right, so we do manual source, and then we're going to click on the face and click on that face. And it said no selection. That's what hung me up last time. And we're going to let it go. So then we should be able to generate a mesh here. And it's not super fine. Okay, good. It looks good though. This is the same mesh that we use. But this thing is bending in this direction, all right, like that. And you don't really need that many elements, okay, to capture that behavior. Okay, so that's the mesh. Now let's talk about the boundary conditions. Well, the bottom of this is fixed. So this is the bottom that we had. So we're going to zoom in. And we're going to click it right here, and we're going to hit apply. And then on the sides, we're going to say this side and this side, those sides, those are going to have the frictionless supports. Okay, because it's as if this is part of a big plate that's being hit by the water. So we come over here, and we click frictionless support. There and there. Whoops, except I had to hold control. Okay? And I hit apply. And now the moment we've all been waiting for, well, maybe not the moment, it's not the climax, but this is maybe like the rising action. We're going to couple the systems. Okay? We're going to couple them. So you see this is static structural, but it says right here, it has an imported load. This is a load that it took loads it took from the fluent simulation. So we're going to insert pressure, okay? And we have to specify where that pressure is acting. That pressure is acting on this surface, and this surface, just like that, okay? And it says no selection, so I better hit apply, okay? And I think we're almost there. Now, in our solution, we're probably interested in deformation, right? We saw that before. And maybe we're interested in stresses. Okay, so we can do von Mises. Okay, let's go ahead and solve. This is the moment we've been waiting for. Will it converge? Was the last 30 minutes in vain? 40 minutes, maybe more. All right, it looks good. Well, I think it looks good. Here's a deformation. All right, so now, do you think that this deformation is causing problems for the fluid flow? Oh, you could say it kind of looks like it could be. But then you come up here and you look at the auto scale, and it's magnified by 2 times 10 to the 7th. All right, so if I do true scale 1, boing. All right, this steel is not deforming. Okay, now is there stress in it? Yeah, there's some stress, but not much. Okay, and that kind of makes sense, right? You've got some fluid, it's not a big deal, it's not causing it to experience that much stress. The equivalent stress is very, very, very low. Okay, but nonetheless, we're happy. Now, what if we change the material to silicone? All right, so here's our silicone. We said, hey, look, the Young's modulus is 1,000 pascals, or 0.001 megapascals, or 1 kilopascal. And structural steel, its Young's modulus is up at 200 gigapascals, right? Big difference. So what we do is we come over here into the solid, and we say, you know, you had structural steel as your default. Let's change it to silicone. All right? And now we can go ahead and hit solve. Okay? And it says it's got large deformation. Yes, it's true. Okay? And if we click on total deformation, whoa! All right, it's bent over. And that is at the true scale. Okay, that's at the true scale. Now, for the lab, what we're going to do is have a graph that you spit out. Well, you don't spit it out, but you plot it. That is the maximum deflection versus Young's modulus. That's the plot that you want to create. So we're going to change the Young's modulus. How do we do that? We're going to parameterize it. How do we look at the maximum deformation? We're going to parameterize it. Okay? So here, if you come down here, for this system, if you click, it says, well, you don't have to click to see, but it says that the maximum deformation is 19.8 millimeters. Okay? So that's about 2 centimeters. We click on this little box here, and it puts in a P. That now means it's been parameterized. We then come over, close, and we go back into the engineering data, and you see now it's got this output. It's going to be the that maximum deformation, and then we're going to go into Young's modulus, and we're going to click on this box over here. And now it will be parameterized. It's got this little thingamabobber here in column E. So we close this, and now we see a loop. And then we go to update all design points. Okay, except we have to, first. Okay, we double click on that. Yeah, it updated, it was the same one, right? And so let's say, I don't know, we want to put in 2,000. Let's say we want to put in 10,000. Let's say that we want to put in 20,000. Say that we want to put in 1e to the 5. All right. Whoops. Okay, it doesn't like that. So I guess I got to do 100,000. Okay. What do you expect to happen? Will the maximum deformation go up or down when we increase the Young's modulus? What do you think? Will the deformation increase or decrease if I see a down, right? I see a couple downers, okay? So let's go ahead and we click update all design points. And unlike some of the things we've done with Fluent, since we're only doing this parameterization on the statics, structural statics, it actually updates pretty quickly, okay? I'm telling you, Ansys, come on, I'm giving you praise here. Please cooperate. Okay. So it's updating. And there weren't that many elements in that beam either, okay? So, and we can look at we see the progress. Oops, it already gave us one answer. Okay, so we see at 2000 we double the Young's modulus, and the maximum deformation went down by about a factor of 2. Okay. And you remember we had those PL cubed over 3EIs, and we had other equations for the deformation with like distributed load on a cantilever beam. Okay. E was often in the denominator. Okay. Often the maximum deformation, the maximum displacement was inversely related to the elastic modulus. So these results do make sense. So your job for the lab assignment is to go ahead and run these types of simulations. Okay. And we see here that it's pretty much a factor of 10 exactly when we went from 1,000 to 10,000. In the last few minutes that I have with you, I just want to share a very quick overview of some of the things that we've done in our lab that have involved fluid structure interactions. And they're very frustrating in many cases. And if you want, you can see a more in-depth presentation that I gave in the spring. It's there for your viewing about things that we've done in the lab. But our lab, okay, is an experimental lab. And we don't simulate everything. And I'll confess, often we do the experiments, we have hypotheses about what things should look like, and then we go back after we get the experimental results, and we have to try to model it to get the models to match our experimental results. Because, we want to say, yeah, we have some understanding of what's going on. That's kind of how the bubble project that I was working on as a PhD student was. All right, and this pattern has continued. Meaning, first I had experiments where I was like, wow, I can get rid of all the bubbles in my spin. Now I have to come up with a model. All right, and so that took extra time. So soft robotics now has been around for quite some time, and I was privileged to work with some wonderful people, very, very creative, very, very smart people who are still contributing. And so this is kind of an example, maybe not so much of a fluid structure interaction, but what you have is air pressure that's going into this device, and it's causing it to deform, and then you can pick up an object. When I came, or before I came to Rutgers, then there was another paper, and this one was led by Rob Shepard, who's at Cornell, that had to do with now kind of putting multiple chambers in a robot to allow it to kind of move and wiggle and look interesting, okay? Again, we were doing these experiments and we were not waiting for people to simulate the behavior. This behavior is pretty complex, okay? But I was involved in some of the efforts to do some modeling back then, okay? And then a little bit later, I'll show you some other stuff with soft robotics, and I'll come back to this if I have a moment or two. When I got to Rutgers, we had a very creative student. Okay, let's see. Where's this stuff? Yes, a very creative student. And yes, we got accused of reinventing the wheel. Okay? So what you see here is a stator, static, not moving in the middle. And it has a bunch of bladders around it. And Kevin had this idea. Okay? And then Shang Yu was the one who implemented a lot of this, and he's the first author on the paper, he had the idea that if you inflated these things in series and had this interesting outer shell, you could get rotation. Okay? And again, we said, okay, well we can make something. If you put the stator on the outside, it's a winch, all right? And if you put the stator on the inside, it's a wheel, all right? And it has some propulsion. So we characterize things as we could, all right? And you can see these things move around. They're kind of fun, like this, right? And it's like springy, spongy, kind of wacky, and quite frankly, it's frustratingly fragile. Okay? Even though it's rubbery, to get these things to work required a lot of time and a lot of effort. We argued that this is something that it has no metal in it. It's perfectly squishy. You can go in water. You can go over rocks. Okay. You can drop it from heights. You can have it roll off a cliff if you like. If you took your car, there are multiple reasons why this is a bad idea with larger objects. Okay. But yes, and then you see a wheel even pops off there. Okay. But we did, again, what I'm saying is we had this behavior that we were interested in understanding, and so once again, we found ourselves running some finite element analysis to say, hey, look, we understand what's going on, right? We took some images of us pressurizing these devices, and then we said, hey, look, this is how they click. But did we attempt to run a simulation with the, with the rotating wheel? No. Okay, that we can let someone else do that. All right, and the mantra that experimentalists or some experimentalists will say is the experiment always wins. Right? At this point in the class, we've talked about ground truth, we've talked about convergence, and when you have a functioning device, sometimes you gotta accept that it works before we understand all the physics and we can model every little itty bitty bit of it. I dream of the day when we will have the ability to have systems that we can. Well, I dream of the day when I personally can have calculations and simulations or something done before we build it. Okay, as an experimentalist, but that's not happening. It hasn't happened yet in my lab. Okay, in our lab, but I hope I have aspirations and I have hopes that one day will happen. We've also spent time. Okay, you can watch the guest lecture. Okay, if you like that professor. Before I knew I would teach this class, Professor Singer interviewed me, and he got other people to contribute guest lectures. And so this is this idea of having these inflatable pieces that we on an airfoil. And so yeah, we did some simulations for this type of behavior that you see here as well. Okay. And look at that. Does this look familiar? Yeah, that's that C-shaped mesh. And then finally, someday we will publish something on this work. Someday. But we haven't yet. Instead, we just had master's theses, okay? Which are really great. So students have graduated, they've had a good time, but we haven't gotten this all straightened out. So what do you think we're looking at here? What does this look like? Okay, a jellyfish. Okay. Is that a real jellyfish or a fake jellyfish? A fake jellyfish, all right? So Daviri and others, Gemmel, a bunch of people, they're still doing research, maybe not on this exactly, but they're very talented researchers, Caltech, other Virginia Tech, Rhode Island. They're very, very talented. And so back in like 2013, 2014, they published this paper saying that the jellyfish is the most efficient, requires the least amount of energy to move underwater, a given length. So for a given size, and the given travel that it can have, it requires the least amount of energy. This is called cost of transport. So we spent a lot of time attempting to beat the jellyfish at its own game. One of the tricks that it plays is that when it puts down its bell, it sends off starting vortices that get going, and that allows it to propels itself. But when it lifts up its bell, it lifts up and it creates what's called a stopping vortex. And that stopping vortex, as the jellyfish is moving forward, it actually catches up to the underside of the jellyfish, and it gives a little boost. So when you look at what's called, this is looking at displacement as a function of time. These are data from them, okay? And you see that there's this propulsion, so you have a high rate, right, initially, then it slows down, and then as it's coasting, boom, that stopping vortex hits the underside, and that gives it a little kick. The jellyfish, these are Arita, and not all jellyfish do the same thing, all right? Right? You've seen squirting animals, you've seen different types of things, right? A box jelly is different than like this moon jellyfish, Arita aurelia. But anyway, so we've been trying, and we haven't worked on it in a while, but we were trying to get similar profile, okay, where you got this bump from the stopping vortex, okay? And then we had multiple people doing fluid structure interactions. Does this look kind of familiar, right? In this case, you're actuating the fin, and we're looking at the vortices that get shed, okay? In this case, experiment, just putting some glitter in water and flapping this thing back and forth. And then this is another jellyfish robot or actuator, okay, that we put in a tank. The tank is still there. The particles may still be in the tank too, actually, but at the bottom, okay, and the jellyfish is moving. So anyway, I hope today, you know, the simulation part was long, right? But building these things takes even more time, all right? But the simulation was really quite limited, okay? It was a 2D slab and not capturing all this interesting behavior, the 3D nature that you have in experience. So I guess we're done, but I will go ahead and put the attendance up. Thank you all for listening.